The purpose of this video is to do some exploratory data analytics using R, just some very basic stuff. We'll show how to create a few visualizations using a library called esquisse. That's the French word for sketch. And that's really what it does. It creates some very simple visualizations, but also provides the code that you would need based on those visualizations that then you can modify if you need to do something more complicated using that as a groundwork. It's kind of the groundwork for it. I'll also show how to get some simple descriptive statistics, things like minimum, maximum, mean, median, standard deviation, and the like. And to do that very, very quickly using just a single command for all of that data, that information. And then finally we'll show just how to do an extremely simple linear regression. Not going to give you lots of detail, but at least give you what the best fit line would look like. So we have all of these types of things we're going to be looking at. So let's go ahead and take a look and get started. The first thing we need is we're going to have to install the package esquisse if you haven't yet. Right, so just go to install. Esquisse is the name of the package, right there it is. Right, and then you click install. Make sure you install dependencies so that is checked, because this will rely on lots of other little libraries that it, like I said, relies on. Okay. Now I've already installed this package, so I'm not going to bother doing that here in this video. If you haven't installed it, you're looking at what it looks like, just click install and you're good to go. Okay, so the next thing I need to do, I'm going to go ahead and open up a script window, just that I'm scripting outside of the console itself. And I want to start that library up. So library esquisse, so let's go ahead and get that run. And that'll take a couple seconds, right, to load or attach, right, that library to R so it can then use the functions inside of it. All right, and then the next step would be this function, which if I try, I can spell it. Esquisser. So E-S-Q-U-I-S-S-E-R, and then you will need an open and close parentheses after that. That will then open up esquisse once we run it. So hit run, and there it goes. So the first thing that will happen inside of esquisse is that it will open up this import data to create graph window. Now at this point, where it says environment, if you already have data loaded inside of R, in this case RStudio is what I'm using, then you can actually just pick which data frame you want to use. Very nice. Except that I don't have any data in R, I didn't bother loading all of that data just yet. So instead I'm going to use an external file. Right? So I go to external file, click browse, and then I can look for whatever the file happens to be. In my case I have this Excel spreadsheet that I'm using, I call it module 2 lab data. For the first thing I want to do, so this, and it immediately knows that it's going to be importing an Excel file. It recognizes that file extension, right? So it is going to use the right functions underneath inside of R to do that installation. Then I get to select which sheet in that. I have several possible sheets. I'm going to do test scores for this first one. So the first task, we're going to take the test scores and we're going to make a histogram out of it. Now I'm going to show a few different ways, I think a couple different ways of doing this and modifying it. Okay. So you can see here test scores, we have student ID numbers and scores themselves, excellent, and then we can just click import data. And there it is. So we have listed here at the very top, there are various boxes. So in our variables box we have student ID listed and we see it's numerical, and score is also numerical. So to create a histogram, it's literally one step. Take score, drag, drop it into the X box. Histogram. Now, it might be that we don't like this histogram. Actually, when I look at it, I don't love the way this is set up. So what it's doing, it is automatically creating a bunch of bins. In our case, it created 30 bins. And we can see that by clicking on geometries here, where it says 30 is the number of bins it created. Now, the purpose here of the histogram is we want to get a feel for the shape of the data. If we have too many bins, it can be very difficult to get that feel. So let me just go to an extreme here. Right. So I'm actually going to change this. Options here, I'm going to change the height because I have to keep scrolling up and down. So let's make this 300 or something like that. There we go, that squishes it some. You can modify options what the width and height are. That is the width and height of the graphic that you're creating. And then geometries is another thing I want to modify right now, and that is the number of bins. I want to make it, first, just for demonstration purposes, what if I make it 100? Then this is what I get. So it takes that range, where we have test scores ranging from, I think the lowest one is 35-ish, the high being a little bit short of 100, and now it created 100 bins out of that, so we're dealing with bins that are like 0.7 or 0.8 wide, and right there's all of our data. This, as it's displayed with so many bins, it's basically impossible for me to read this and get a sense of the overall shape of the data, which is really what the purpose of the histogram is, for me to get a sense of the overall shape or distribution of this data. Too many bins here. So, and that is something that will happen here. You'll end up with lots and lots of little, so here's this 1, 1, 1, lots of these things, which is just difficult to read. So, fewer bins is going to improve that. And I could try going all the way down to 10 bins. Now in this case, the shape of 10 bins isn't terrible, actually. Like, it lets me get a sense of the overall shape, kind of what kind of symmetry there is, and the like. So this isn't too bad. One thing that can happen, though, is if you go with too few bins, you can end up with a very flat distribution. Now, sometimes flat distributions actually exist, in which case it's not a problem that it's flat. But sometimes a distribution that isn't actually flat appears flat when we lower the number of bins too far. And that should be obvious. For example, if you just have one bin that covers the entire range, well, it's just one bar. Right? Cut the thing in half, these two are probably going to be similar in height. Right? Cut it into 4, now we're getting to where we might start seeing a peak in the middle and perhaps something smaller toward the edges, kind of tails off of the edge if we have something that's normally distributed. But if you cut down the number of bins too far, we totally lose the distribution. So here, 10 isn't terrible, so you can certainly play around with this. It's very easy. Just take the slider and change the number of bins and just move it around to see where you think it's easiest for you to see the overall shape of the data. So that is something that we can do here. Now, one issue though, right, with this automated histogram is that the cutoffs are sometimes not very, let's say, human-friendly. So that's an issue, potentially. Right, so we might want to go through and actually define our own cutoffs and say, no, we want a particular range, like this range over here. It looks like it's something like, what is it, like 38, maybe? I don't know, like 37 to 39 might be this range. These are really awkward numbers. I would like to have more control over that. It turns out that's something we can do by creating bins. Now, if you have watched my video about frequency tables in R, you know what we're going to do. We need to use the cut function. However, we're not going to leave esquisse. Esquisse actually has the cut function built into it, where we can use it very easily in a graphical interface. So up here where you have the scissors and 1, 2 right there, click on that, and it brings this up. And it gives us a number of ways that we could try to cut the data and create these bins that we want. Now, I'm not interested in student ID, so I'm going to change this over to score. Now the method. Now the first method you can see it's listing as quantile. So what it's going to do if I use this method, so quantile with 5 breaks, so it divides things into 1, 2, 3, 4, 5 groups. So it's going to divide things up so that 1/5 of my data is in each of these. Now that means that these breaks are not equally spaced. So you see there's one here that looks like about 50, I can scroll down a little bit. So 34 to 59 and a half. First one, and then we have 59.5 to 68. So we have a range here of like 25 for the first bin, but less than 10 for the second bin. And then the third bin is even narrower. It's 68 to 74.5. Right? So this is not going to be useful for me, and you can even get a sense of what the shape of the distribution will be when you look at the counts. It's going to be extremely flat. The problem here is that the bins have different widths. Okay, so that's not going to be very helpful. So instead, there are other options. Right? So one option would be, if I want to define them, I can choose fixed. And then I pick the number of breaks there are, right? So in this case I'm choosing 5 breaks, say, and then I can move them wherever I want. So in my case, since I know these are test scores, I might want to put them somewhere where, say, letter grades change, right? So say just below 60, because at 60 you move from F to a D in a 10-point scale, then say just below 70, at 70, you switch from a D to a C, just below 80, and just below 90. There we go. So this would work. Right? So this is one way we could do it. If I was happy with this, I could scroll down here, create factor variable, and that will create the bins that I want. But I'm not going to do that, because there's in fact an easier option here as well. Right? it's going to be even more human-friendly in terms of the cutoff points. And that is if you choose method, like go ahead and you can play with these if you want, that's fine. Right? What does equal do? Right? What does equal do? Well, you can see equal, it's creating equally sized breaks. Okay, that's kind of nice. Right? But again, I'd like to have some control over where those are, make them human-friendly. Pretty is tempting, and that is exactly what I want. Because what pretty does, right, based on the number of breaks you tell it to do, now first thing, it will violate this number of breaks in order to guarantee the prettiness of it. So in our case, you can see that it's choosing breaks every 10. So we have ranges of 30 to 40, 40 to 50, 50 to 60, and so on. This is beautiful as a human being, I love it. Right? And now if I change the number of breaks from 5 to 6, you can see that doesn't change, because it had already established more than 6 breaks. For me to get things to change, I have to increase the number of breaks to the point where instead of saying, oh, let's count by 10s, it says, let's count by 5s. Oh, there we go. Right, so when I get the number of breaks up to 10, right, now it's going to go from 30 to 35, 35 to 40, and so on. I don't want that level of detail, so I'll turn it back down here. The exact number of breaks doesn't matter because it's going to make things multiples of 10, and that's what I want. So I'm happy with this, I create factor variable. So now histogram based on that factor variable instead, right? So I'm going to pull out the number score, I'm going to pull it up into the variables, again, that makes us have an empty histogram, then I'll take score cut, drag it down into X, and you can see it converts to a bar graph. Right? That's because score cut, you can see it has AA here, it's reading as character data. That's perfectly fine, right? The characters are telling us exactly what we want, that is the range of 30 to 40, 40 to 50, 50 to 60, and so on. So this is still a histogram, even if it's not called a histogram by esquisse. So this would be one way that we could do this. So then if you want to get this out of esquisse, so that you're actually like using this bar graph somewhere, easy way to do that, if you right click, it brings up the option to copy image or to save the image as something. So these are all things that you could do to pull the image out of esquisse, put it wherever you want to actually use it. One type of image we can create these histograms. Now let's create a time plot using the line graph option. So for time plot, these scores, this data doesn't make sense. So I need to go back and import different data. Where it looks like a stack of coins or something like that, that's the import data option. And again, external file, I'm going to use that same file as before, but this time I'm going to select the Canton-Maslin employment data, which is divided, you can see, over time by months, and then we have the level of employment. Okay, that's what I want. So let's go ahead and import that data. Now you can see when I do this in esquisse, it gets rid of the old data. It can only deal with one data set at a time. So that's a limitation to be aware of, which you don't have, say, if you go back into RStudio in general. Okay, so in order to create our time plot as a line graph, very simple. Take month, drag, drop into X. Employment, drag, drop into Y. You can see it makes a line graph here, and there's what that line looks like. You can see this data was not seasonally adjusted, so you can see seasonal changes as there are increases and decreases in employment at various times of year, right, peaks, valleys, and so on. We can see this is the COVID shutdown that happened in early 2020, around I think March, April was when employment just tanked for a month, right? So this is what things look like during this period of time. So fairly straightforward. Now I want to tell you a little bit about some of the options, since we didn't do that with the histograms. Right, so I mentioned options before. This changes the height and width of the graphic itself, which is naturally going to change the feel of it and could potentially make it fit wherever you want to copy and paste it to better. You can also add titles, subtitles, caption, X and Y labels. So if I don't like employment as the label here, or let's say employment is a good label, so I'm not going to do that. But Y label, maybe instead of month, I want it to be time or something like that. Right, so I do that, and then it's changed. Okay. Let's try reloading this, see if that works. And I killed it. Oh, here we go. It's thinking. All right. Well, apparently that did not do what I thought it was going to do. Let's get back to where we were. There's something going on down here. All right. Let's try this again. And, again, I'm not going to cut that because sometimes you do something that you think is going to work and it doesn't work quite like you thought it would. So, so you just kind of have to laugh at yourself, go back. Very few things can we do that are not recoverable from. All right, so month and employment, there we are. Okay, there it is. So this is a point where I'm not entirely. Oh, I bet I know what I have to do. Let's try this. Time. What happens if I have the plus sign here? It gives me some additional details, but does it actually change? It's not changing the for some reason. Well, based on the code here, it should change that label, so I'm not entirely sure why it's failing to do that. I don't know. That's something we learn. Okay. Does it actually add a title if I do it? Okay, it's employment over time. Looks like it did actually add that. Employment over time, it does actually add that label. Interesting. If I eliminate it, let's go away, okay. Yeah, all right. Oh, wait. It did change time, but it's for the Y label. Okay, I'm sure there are people on YouTube just screaming at me. No, it's supposed to be on X. Okay. There it is. Okay, employment on Y, time on X. Yes. Okay. Axes. So here we can change things like things like the text options. Very useful for us. In our case, this is rational data. Rational data will often just kind of naturally, the way that we interpret it in our brain is we treat the bottom as 0, which means these graphs can be really, really misleading if the bottom is not actually 0. So this makes it look like, just at a glance, oh no, right, March 2020, literally everyone lost their job. But that's not true. We still have about 160,000 people, right, that are still employed at that point. Right, so I'm going to go ahead here. I'm going to change the y-axis limits, y-axis, right? So I'm going to make the bottom 0 and then make the top, around the top of our data, 210,000. Okay, close that up, and there we go. So now we can see those changes. Well, there's certainly a big drop there comparatively. It is not like everyone lost their job. There's a lot of space underneath here indicating people that are still employed. All right, so we're good. Geometries, here we can do things like if you like changing the line color, so you want it to be orange or red or blue, or you can do that. You can also change the width and the type, right? So if I want it to be, say, dashes, you can see it changes to dashes, or a theme. This will modify mostly the look of your grid lines, right? And also if you have a legend somewhere where the legend appears, you can see how it's justified and the like. In our case, we only have one variable that's showing there, so it doesn't feel any need to add a legend. But we could do things like change the theme. So if you change it from minimal to, say, gray, see now the background is gray. Or light. So now the background is somewhat light. Line draw, that makes the axis lines much more prominent, I would say. Right? Minimal, I like minimal because you do still have the lines there in the background, even though they're fairly faint. The data, well, this allows you to filter the data, and this would be very useful for us in this case if we wanted to narrow down to a specific time frame. Right? So say we want to focus in on what happened during that time period from 2019 to 2021. So I can just select those months, and right there, you can see it narrows things down. So it's a very easy click and drag to filter the data. It can also technically, this is not as useful for our purposes, you can filter the data along the y-axis, right? So if say I thought that, say, these lower values were that I want to cut off, I could say, okay, only show the data that's above that point. And then you can see then we lost the big drop that we had then in March of 2020. All right. And then finally, code. What this does, this allows you to either copy and paste this into a script, or using copy to clipboard, that just copies it like we would normally think of copying, or we can insert the code in the script. So if we have a script file open in RStudio, if you click that, it will automatically put all of this code into your R script. And that's really nice if you're going to be sharing some kind of visualization with somebody else. then this is a nice way to do it if they're going to be creating that visualization in R, and this allows you to recreate also whatever you did in the past. It very easily will do this for you. All right, so I'm going to go ahead and close that off there. I don't need any of these options. If you want to pull out this graph, you can again. Right-click and copy the image or save it as. It can save it as, it doesn't actually tell me what the file type is. Okay. Next thing, another type of graph we might want to create is a box and whisker plot. It's another one, it's just based on a single variable. So let's go ahead and do that. Part of the data set that I had where I gave a survey to the faculty after a meeting, and I want to know some of their opinions about different things that happened in the meeting. Right, so let me go ahead and load that data. Okay, so in this case, it's faculty survey. All right, so I'm going to go ahead and import this data. All right, now what I want to do is look at how long it's taking people to take this survey, so this duration data. Now I have a problem when I start out though, and that is it says duration in seconds, but this AA here indicates it's reading this as character data. The problem is in the original data file, it's not just one line that is a description. There are a couple other lines that are also just information that came through from the survey site that I used. It's not really useful to us though, and the problem is that it makes, in this case, esquisse, but R in general, think I'm dealing with character data because there are some words in the first few lines. So I need to fix that. So, several ways we could do this. I'm going to do it the easy way. And that is, right here, there's the option to update variables. Click on that. And then what I can do, the check marks here allow me to select which variables I want to include. I'm only interested in the duration. So I'm going to click that, and that'll get rid of all these other things I don't want. Then class. Class is the type of data you're dealing with. I can change this by clicking on select new class and choosing numeric. What this is going to do, it's going to create, in effect, it's basically an error code, what they call an NA, or not applicable, not available. Right? It'll create NAs for anything that it's reading as characters, but that's fine. It doesn't really change the things that I'm interested in. So we'll go ahead and apply those changes. So you can see here, the only thing I have now is duration, and it is reading it as a number. I'm going to drop it down into X. Right. Now the first thing it does is create a histogram, which is all well and good. It also gives me a warning here that it removed a couple of rows because it says non-finite outside the scale range. That's because it's NAs. One thing I can do to fix that, get rid of the warning, under data, there's this option here where it says NA. You can't really read the A from here because of the narrowness of this window, the way that I open it. So, but that does say NA. If I turn this off, there we go. Now the NAs aren't there anymore and the warning goes away. So it's just filtering out anything that would be an NA. Okay, so I have a histogram, but that's not what I want. I want a box plot. So if I click on histogram here, it brings up a number of options. Now if I go down far enough, unfortunately I don't have it big enough to go down far enough. It's not going to let me scroll, is it? Ugh. Alright, well, I'm going to pause the video and I'm going to reopen everything so that I can actually get the selections that I need. Okay. I'm back in your time, in less than a second. And we're back. Alright, so you can see it's probably significantly harder to read, which is why I zoom in on this thing. But in any case, where it says histogram up here, right, if I click on that, it brings up a number of options, including one that says box plot. So if I click on box plot, there we go. It creates the box plot that I want. Now the way that this displays, anything that's a dot, it has identified as being a potential outlier based on what they call the 1.5 times IQR rule. Right? So it's really looking at kind of what is the range here within the main part of the box, that is where half of your data is all within that range. So the center half of the data is all within that range. Anything that's more than 1.5 times that width outside the box, right, is considered an outlier. So in this case, we have a few outliers on the upper end. Now the box itself, like the top of the whisker would be the maximum excluding any outliers. The bottom whisker would be the minimum excluding any outliers. Then you have the top quarter of the data with that whisker. Then the box has the center 50%, and there's a line in it, which is not too easy to see with this particular coloration. I'm going to change the color to make it somewhat lighter, and then you can see the center line significantly more easily. Right. So then we have, here's our median, then this would be from the median, this would be kind of, what is the second quartile, right? So we have the top quartile, and then the next quartile, and then the next quartile, and then finally the lowest quartile. So that's the way that divides that up. So it gives you another way of kind of looking at the data, where does most of the data fall, and so on. Now, one thing to keep in mind is that when you have outliers like this, that will have an effect on the mean of the data, which could be something that might be an issue that you'd want to think about as you analyze the data. All right. So what else would we like to do? Well, one thing I'm going to do, I'm going to zoom back. No, let's keep the zoom out just in case I run into other issues. So there we go. All right. It's not an ideal view, but we'll zoom back in before too long. Right. All right, so let's go ahead, and now the last one I want to create is a scatter plot, which is a common way of displaying data that has two dimensions. Right. So in my case, I have some data on two different tests scores from the same set of students. So the question is, basically, did students that did well on the first test also do well on the second test? Is the kind of answer I want to try to get from this. Right, so again, I'm importing the data. In this case, it's test data 2. It has student IDs, test 1, and test 2. And then I'm going to go ahead and import. To create a XY scatter plot, all we have to do, take test 1, I want that to be my X variable, test 2 is my Y variable, and there we are, and we have a bunch of little orange dots. I don't like the orange, I'm going to change it to that deep blue. And there we are. So then we can see it does look like there's generally an upward slope here. I would like if I could get more precise with that, though. Like, I would like some kind of best fit line. Now here, in order to do that, what we're going to have to take advantage of is that you can add additional layers to a graphic inside of R, and esquisse allows you to do that. So right now you can see I'm up here, I'm GOM1, so that's the first layer. So I'm going to go to GOM2, being our second layer. So again, I want this to be X and Y, right? But instead of having the type of plot be a point plot, which is what we have before, I'm going to choose smooth. Now this is going to take a minute, and then there we go. So it adds this line in, which is a smooth line kind of showing what the overall trend is. Now there are a number of ways that can calculate this. This one is called a less line. Right? I think it's less is how I would pronounce it, right? Which is based on, it's smooth, but it's also based on kind of local relationships that it sees, right? So the slope of the line here is based on the points that are near that particular part of the line. So what this would allow us to do is to see if there is a change in that relationship. So it looks like, for example, those that did, say, within this range on test 1 actually improved their score significantly on test 2. But as you move toward that range, it looks like people just decide not to study as hard or something. But then you have the more positive connection. Once you get, looks like a score about 65 or higher, right? It's a more regular positive connection. Now there are other ways that we could estimate this. So under geometries, we have the choice. So there's less as our first option. LM would be a linear model. You can see that just gives us a straight line here. So it gives us what is the best fit line. If you're familiar with regression at all, which we'll talk about regression more in a minute, that is the line right from the regression right here. GAM, this would be a generalized additive model, where what it does, it takes a number of polynomials and adds them together, so you end up with a curved line. Right, so there we go. So you have a curve to it here, and this is capturing the fact that it looks like it's relatively flat down here in the low values, but then becomes somewhat steeper once you get to a score around, about 65, 70, something in that range. Now, this band around it is based on a confidence interval, right? So what we can really interpret this line as being is if your score is equal to whatever the test 1 or X value is, then that would be, on average, what we'd expect the scores from students with that particular test 1 score to earn on test 2. What the gray bar is it gives you the range that average probably falls within. Now, I don't like having that confidence interval there. I think it takes away from being able to see the line. So it says display confidence interval around smooth. It's another geometries option. I'm going to turn that off. You can also control some things like you control the amount of smoothing for GAM, or as we turn that down and up, do we see any significant changes in the last line? I don't. That might just be a GAM option then. So in this case, apparently the degree of smoothing here doesn't make how that happens. Okay. All right. Oh, I'm going to switch that back to the linear model since we're going to be. Okay. So that is that in terms of just a handful of visualizations we can create. Esquisse also has a number of other options that you can use. Really, if you just play around with the options that it has here, you can see a number of possibilities. I'm going to go ahead and get out of esquisse and zoom back in, and then we'll see some other things we can do inside of the RStudio environment. So go ahead and, I'm going to pause the video. I'll be back with you in, from your view, 2 seconds. All right, we're zoomed back in. So let's go ahead and do a little bit of more descriptive statistics inside of the RStudio environment. So the first thing I need to do is I need to actually load the data that I'm going to use, because I didn't do that within the R environment. So I'm going to import the data set. The first thing I'm going to do, I'm going to do the faculty data. Okay, it's going to take me. Importing data just as we normally would inside of RStudio. So choosing the import data option and then navigating to where my data file is, and that's what's taking me the time here. Oh, there it is. Okay. Now, one issue we're going to run into with this data, I want to go into faculty survey. Now we know the problem is that it's going to read this duration, which is what I want to use. It's reading it as a character. I don't want it to read as character. I want it to be numeric. So if I click on the caret here, you get the kind of like triangle V sort of shape. I can choose numeric here, and then it will automatically go through it. It NAs anything that is not a number and converts everything else so it's going to read as a number, which is going to be useful for me when I'm calculating things. So once we've done that, import. So we have our data all loaded here. First couple are NAs, but everything after that are numbers of seconds. Excellent. So the next thing I want to do, I want to create a descriptive statistics, just list of the types of descriptive statistics we would like. Now I could go through and there are functions for mean, for median, for standard deviation, for skewness, for kurtosis, and all of this. I don't want to do that. Instead, what I want to do is have it create all of that at once. To do that, I need to use the library summary tools, which I've already installed. If you haven't installed it yet, install that. So install the summary tools, then we run the library function to attach it. Right, there we go. And then it's DE. That's what we need. Okay. So that gives us the descriptive statistics, then we just need to tell it what data frame I'm using. So I'm going to use module 2 lab data, right there we are. And then which variable I want to use. So I'm going to give it a $sign to tell it I want to choose a variable, and I'm choosing duration in seconds. And that's that. And then go ahead and run that, and it gives me this. Right, so it tells me, like, what is the mean? What is the standard deviation? What's our minimum? What's the first quartile cutoff between the first and second quartile? What's the median? Third quartile cutoff? What's the maximum going to be? Right. It's mad. I'm not entirely sure. I'm guessing that's the mean absolute deviation. So looking at the difference between each value and probably the mean, and then just taking it as a positive value and averaging that all out. I'm not positive on that, but that'd be my guess. Let's see. IQR would be, again, what is the difference between Q3 and Q1, which would be CV would be the coefficient of variation. That is a measure of how volatile your data is based on taking your standard deviation divided by the mean. Skewness here, right? So positive number here indicates we have a positive skew, so we do have some outliers potentially off in the positive direction, so they're higher than most of the data. Kurtosis here, we do have a fairly high level of kurtosis as well. Now typically speaking, the skewness and kurtosis, there aren't real strong guidelines as to what's considered normal or not. Normally I see numbers around 1, 2, 3, kurtosis maybe up to 5, something like that. This also tells us the percent that's valid, so this is telling us that we did have a few NAs in there that it was not using in these calculations. Okay, so it's a real quick way to get some good descriptive statistics in a numerical summary. Now we can use this type of thing to look for normality. So for example, I'm going to open up the test score data in this environment and check that. Right, so I'm going to do the same kind of thing I did before. So import from Excel, and then I look for my data file, which again takes a few seconds. I have to navigate my file system. Lab data. This one I'm going to change the name of my import. This one I'm just going to call it test scores, maybe? No. I'm going to want to use test scores later. Oh no, I can call this test scores. That'll work. And that reflected test scores here. Yes, that's what I want. Okay, so let's just have a list of test scores. Excellent. And then import. Alright, there we go. And then again, so what I want here, again, it's just the descriptive statistics. This time it's from test scores. There we are. And I want to select scores. I'm not really concerned about the average student ID number. Okay, and then we'll run. And there that all is. So then I can look. Now to check for normality, the big things you'd look for here would be skewness and kurtosis. That is, are they reasonably close to 0? That's a big thing to look for. Another thing you would look for is not just this, but also at the histogram that we created before. That is it symmetrical, for example? Like, does it have kind of that bell curve sort of shape which normal data typically has? So you can look both at the visual, the histogram that we created at the very beginning of this video, as well as these numerical summaries. Some sense of, is this data roughly normal? Another thing we can do, in terms of calculations, would be to create a correlation matrix. Right? So this is going to be useful for things like, say, employment data. So I'm going to go ahead and do that. So I'm going to open again. Again, I'm importing data from. Now this data is again looking at employment data for the. I'm in the Massillon Canton area in Ohio, and I would like to know, is there a strong connection between Ohio's level of employment overall and that between the area in which I live, Canton, Massillon, right? And also, what about the U.S. as a whole? Right? And this is something. There's actually a built-in function that allows us to do this very easily. So I'm going to go ahead and load up that data. Oh, I made a mistake because I just hit import too quickly, didn't I? So, yeah. This one I want to call this employment data. My employment data came in well. Oh no, that's the wrong one. Let's try this again. For the third time's a charm, right? Alright. Again, like, I like to keep this stuff in really for two reasons. One, I hate editing videos. I'm not going to lie about that. But employment data is what I want, but it's not the employment data sheet. It's what I want is the Canton-Massillon employment data. There we go. So this will overwrite that data frame with the data that I actually want. Let's try that again. So view this. Yeah. It's like I'm going to have to go through, I'm going to have to remove that. Oh, I can easily do this. So I'm widening this. You can't see this on your end, I don't think. But there's an option to clear objects from workspace, which I'm going to do right now. That clears out everything from my workspace. Let's see, all right. Yeah, it's something it appears off to the. Oh, actually, I might be able to do this. It clears objects from workspace, which just clears out any of the data frames you have in there. Since I know I'm not going to be using the other ones, it's not really. So, again, fourth time's the charm, right? Okay, and so I want it to be Canton-Massillon employment data. I will change the name here to employment data. Don't have a good explanation for why it is doing that to me. All right, well, let's try calling it something else. I think I really wanted it to be named that, but oh well. So I guess CM employment or something like that will work. All right. CM employment. Excellent employment data and import. Okay, this is odd. So it's like it's stuck on this employment spreadsheet. That is weird. I'm going to pause the video here to see if I can figure out what is going on with that. All right, so I'm just apparently dense. The employment data that I originally loaded was the correct one. I just got mixed up in my brain because you can see right here when it says employment data here, it does have U.S., Ohio, and Canton, which is all the stuff that I want. All right, now whatever. So we're going to go ahead and. Now, in order to get the correlation, I'm going to come back here to my script file. Script file, there we are. What we need to do, we just use this line. It's COR, that does correlation, and then I want to look at the employment data. Right. Now, the problem is if I tried to run it as is, it's going to give me an error. So I'll go ahead and show you that. Right. So it says X must be numeric. So the problem is that right now in that employment data, some of, well, like the first column of it, if we look at it closely, you see is dates. And dates do not read in as numbers. So what I need to do is leave out that first column. So I add in the brackets here, and then a comma. So because I have nothing before the comma, that means it's still going to read every row. And then 2:4. That tells it to read the second column through the fourth column, which is all the employment data that we want. So let's go ahead and run that. There we go. We've got it. Right, so now it's showing us in this kind of tabular form, right, how the different things are connect with each other. So the way you read this, say any number here, you look at what column it's in. So this would be the U.S. employment column, and what row it's in, the Ohio employment column. So the correlation between the U.S. employment and Ohio employment is 0.9155. That between the U.S. and Canton is 0.4983. Right? Between, say, Ohio is 1 because you're perfectly correlated with yourself. Ohio and Canton would be 0.76. Right? So that allows you to very quickly see all these different correlations between anything you happen to have in your data set. Now, the last thing I want to do is to do I'm going to load up the test data 2 again, because I want that to tell me, remember it's the one where we have the test score 1, test score 2 for each student. So what I want to do here is to actually get an estimate of what the, okay, test data 2, right, I'm just going to call this test data 2. To do is get an estimate of what that line actually looks like in terms of what the formula is. So I'm going to go ahead and import the data here. There we are. Now the line I'm going to use, it's LM, it's linear model, and the form of this is first you say, what is the thing you're trying to explain? Right, so for me it's test data 2. Data 2, test 2. Right? I want to explain by, you put a tilde then, this is a little squiggle, and then I want to use test data 2, test 1. Right, so what it's going to do is find what is that linear form, so intercept plus slope times, in this case, test 1 scores, that gives you the best prediction for the average test 2 score. Okay. All right, and then we can just run that correctly. It tells us here's the intercept in our linear form, so y equals, there's an intercept plus our slope times the value of test 1. So real quick, dirty way to get your best fit line. Now there are lots of details about this that you can get using some other methods. I'm not going to touch those right now. We're trying to keep it super simple. What does this relationship look like? Just quick and dirty. This gives us the idea. All right, so I'm going to end the video there, and